driving and in like speech recognition, all those have in background somewhere like the CNNs which are like actually a deep learning working on the background that has led to all these improvements and able to make it like market ready where like everyone can use it. In the pre-deep learning era, it was like not possible to have such a good accuracy in these different tasks. So if I have to look into the brief history of deep learning, one of the major success actually came out in 1998, where you can see the picture here. I will just turn on my laser. So this picture is actually of Jan LeCun, who is a professor in New York University, NYU, and he came out with this network called LeNet. So Lee stands for his name LeCun, and net stands for network. So in LeNet, what he used was convolution neural networks for handwritten digit recognition. So by handwritten digit recognition, you can see something like the 4 is written in hand in an image, and like the network has to identify like what is the letter written. So it was only digit recognition, so it varied from like 0 to 9, 0, 1, 2, 3, 4 up to like 9. Even like before like 1998, it was like very difficult to do, even though if you think of like it's not a difficult task if we particularly get it like consider compare it with problems such as like detecting humans or particularly like faces or something like that. Like recognizing like digits was somewhat more easier because it has like a fixed features of how a 4 looks, how a 3 looks, or how a 7 looks. Although like it changes obviously a little bit here and there based on like each individual person's writing, because these are not something written by computer, but these are handwritten. So he came out with convolution neural networks in 1998, which was like immensely successful and achieved like very good accuracy. And even like, I think like still now for a long amount of time, his network was the one which was used for like all the cases of like automatic sorting of letters in the post office and everywhere. But however, after in 1998, still there was like not too much success other than this handwritten digit recognition. Not too much success in other fields of computer vision of, let's say, like detecting like cars or objects such as like cats or dogs. But then another major breakthrough came in 2009 when the first ImageNet challenge was organized. So the picture that you see here is a professor called Fei-Fei Li, who is an professor in Stanford University, and she and her entire group came out with a challenge called ImageNet. I will be going through the little bit of this challenge, but what it had was it had an immense data set of millions and of pictures which were like annotated, saying like usually in 1,000 classes of, let's say, like this is this type of dog, this is a cat, this is a car, this is a bus, truck. And since it was 1,000 classes, so you can just assume like estimate like how many different categories of images this challenge had. So this was one of the first large-scale data set which was provided to the entire research community. Beforehand, there was like not too much of large-scale data sets available, which were like annotated or labeled data set. But then after in 2009, the first ImageNet challenge came out. In 2012, AlexNet, there was this network called AlexNet, which was proposed by Alex Crisby, which won the ImageNet challenge. And this was the first time when actually like the sort of this deep learning was used in the ImageNet challenge. And the picture that you see here is Jeffrey Hinton, who is a professor in University of Montreal, Canada. And his group was actually comprised of this Alex Crisby. And they came out with this AlexNet, where they successfully applied, again, like convolution neural networks back from 1998 to win the ImageNet challenge. And they were the first one to actually use the GPUs, because right at those point of time, GPUs started to come in, but they were mostly used for different sorts of like gaming purposes and not too much in any of the other researches. But he and his group showed that GPUs can be used to use this large-scale data set that came out with the ImageNet. And then he and his group won the 2012 ImageNet challenge, and the success that was like shown to achieve in this ImageNet challenge blew out like almost like everyone's mind. And after that, like the entire craze of deep learning started. So if I have to look into this ImageNet challenge, So it was a classification data set. So it meant that you have a lot of images. So suppose like 1.2 million images that was actually in the ImageNet. Each of this image you have to classify into like 1,000 categories. If it is a dog, even in dogs, they had like many varieties of dogs, cats or bus, truck, different other things. So in this ImageNet challenge, when it came out, so this graph that you are seeing here is basically showing you the x-axis, the different tiers, so like 2010, 11, 12, 13, and the y-axis showing the percentage of, so something like how much error that it's doing. So the higher the value is, the worse is the model. So if you see in 2010, the winner was at an error rate of somewhere around like 26 or 28%. But however, there was a lot of variance between each of the teams' accuracies. Like it varied right from around like 80% of wrong answers to up till like 28%. Even then, after in 2011 also, the same thing happened. The accuracy reduced a little bit, but still it was like more than 25%. Then in 2012, actually this AlexNet came out, and the winner of this 2012 that you are seeing here is the AlexNet accuracy. And this was the first time that the accuracy went below like 25%. And this was also the first time when like deep learning was used, which resulted to the immense, if you can see the performance of all the other teams in 2012 was, and the performance of AlexNet, they were like far better compared to all the other models. So at that point of time, actually, like people saw that how much reliability or scalability that this or potential this model had. And then in the next years, almost like every team used some sort of this deep learning or convolution neural networks in their models. And therefore, if you see that not only the errors also decreased, but other thing is that the variance that you are seeing in all the previous years, they went out, and you can see here that everyone were almost like very close to each other. This was like also one of the important potentials that was seen in deep learning, that previously people used to do all this hand-picked features, which resulted to like, depending on how you're picking the features, your accuracy can vary a lot. But here, since it didn't had any sort of this hand-picked features, which we will look through later, that resulted into like everyone having like very good accuracy. And after that, it went on in the next few years. And in 2017, actually like 29 out of 38 teams got like only less than like 5% wrong. So everyone was using deep learning and showed like a immense improvement in accuracy compared to what was happening in the just before the AlexNet came out. Let's look into like why we will not be using. So neural networks has been there for a long amount of time. It had actually built a lot of praise in sometime in 1980s and in the early 1990s, but after that it somehow died out. And then support vector machines was one of the most popular classifier that was being used at that point of time. So why regular neural network was not so much successful in doing this task of image classification or working on these images and or speeches? So one of the primary reasons was images, in contrast to some of other problems, they are extremely high dimensional. So if you look into even a small image, right now the image pixel size can be like, let's say like the 1080p or 1920 pixels. But even if you just consider an image of like 227 cross 227 cross 3, so 227, let's say the height, 227 is the width, and 3 is a channel. So usually images, if they are like RGB images, they have like 3 channels. So now if we have this regular neural networks, then how it used to occur is like each of these pixels. So I'm just showing a smaller scale version here of, let's say like 9 cross 9. So you have like each of these pixels as A1, A2, A3, A4, B1, B2, B3, something like that. So how neural networks used to work, traditional neural networks, is like for each of these pixels, they used to have like a separate weight. So therefore, since you have so many pixels, the number of weights would be like immensely large. So a small size image, even this 227 cross 227 cross 3, this is actually not just a random size actually. So this 227 was actually the image size that was used by AlexNet. So even with this, if you have just one layer of neural networks, you would get something like 154,000 weights. And if you have like multiple layers of neural networks, you have like multiples of this 154,000 weights approximately. And if you have like so many weights, the chances of overfitting your model becomes like extremely high. So therefore, like it was like not, that was the primary reason why it was like not so much successful. Some of the other reasons why neural network was not so much successful, because it doesn't have an inbuilt variance to translation or distortion. What do I mean? Like, let's say like how a person writes like 7, that can change differently. So let's say a 7 can be written like this in an image of here, but 7 cannot be also written if we have the image here. It can be something like that. In distortions, where like if you are using pixels, each pixel separately, each pixel having individual weight, then this doesn't work with these images. And further, also like images have some sort of local structures, some sort of like edges. So if I have to find out like 7, they have like edges here, they have edges here, and they have edges here. So these are same. If we have to edges or corners, we will be looking through the entire of these images. So this was not in regular neural networks, because they had like different weights for each of the cases, whereas the tasks that we are doing might be same in different parts of the image. So these were some of the reasons why the regular neural network was not so much successful. So what happened is this convolution neural networks that finally came out, and they tried to alleviate all the issues that were present with the regular neural networks or fully connected neural networks. So what does CNN had? CNN had actually like 3 main features. One was the local receptive fields, the second was the shared weights, and third was a subsampling or pooling. I will be going through each of this separately. But what does this local receptive fields do? As I said, that irrespective of, let's say you have the image here of the car, so you have to find out the edges or the corners. So finding out the edges or the corners, you have to do in like different parts of this throughout this image. Okay, so what this local receptive fields will do is to extract such of these basic features which can be present in any part of the image. Okay, so you have an edge here, you have edge here, and in all the other parts. So finding out these edges will be done this local receptive fields, because they are like completely local and not global throughout the entire image. And then usually CNNs had like, as like regular neural networks, they had like multiple layers. So the lower layers will do all this basic features recognition, whereas the higher features will be usually doing all this higher layers. So after getting these things of this, let's say the images, this edges or corners, then the higher layers might be looking into where are the wheels present, something like that. Okay. So, and another important feature was this weights that we will learn will be shared spatially in images. So let's say you have, I will be just going through, let's say you have this local receptive field that you are seeing here. So this same filter will be used throughout across the image. So the weights of this filter will be shared spatially across the entire image. And when we are doing actually in speeches, they will be shared temporally actually in time. Okay. So that's what CNN used to do, and this was achieved using the convolution and layer. So that matrix that you are seeing consists of this weights, this smaller filter. This is actually called a convolution layers. And this is the paper that gradient-based learning applied to digital recognition by Jan LeCun, which actually proposed and first successfully used CNNs in handwritten digital recognitions. So let's look into what is this convolution layers. Okay. So because this is the main thing in CNNs. So if you have to look into like convolution layers, so let's say we have an image of 32 cross 32 cross 3. So 32 cross 32 is also not a random number. It was actually the size of the handwritten digital recognition dataset, which was called the MNIST dataset, which Jan LeCun used. Although the MNIST dataset was just a grayscale image, so it had like just like one depth instead of like 3. But usually if you have like RGB images, it has like 3 channels of the red, green, and blue. Okay, so let's say that you have a small size image of 32 cross 32. So 32 is the height, 32 is the width, and the depth is like 3, which correspond to the number of channels. Okay, now you have a filter which is of a much smaller size compared to the image. So when the image is a 32 cross 32, the filter is, let's say, like 5 cross 5. The depth will be the same. So this filter will be passing through the entire depth. So since the depth was 3 in the initial image, so here the filter will also have the same depth of the 3. So this filter, this 5 cross 5 cross 3, will consist of these weights that I had actually shown in the last. So this is like, let's say, like a 3 cross 3, where like each of this has like a different weights. Okay, similarly this 5 cross 5 cross 3 will also have like different weights for each of this size. So the total number of weights that we'll have in the filter is 5 into 5 into 3. Okay, what it will do is like this small filter will then, for every location of the image, so let's say like you have like this location in the image. So at this location you have like 5 cross 5 cross 3 pixels extracted from the original image, or the green image, or the green portion. So which will be represent as X. Okay, and the W is basically the filter weights. Okay, so you have the W transpose X. So W is also a 5 cross 5 cross 3, and X is also of the same size, but W is taken from the filter while X is taken from the image. Okay, and this is actually just what neural networks also does, like W transpose X plus B. Okay, where B is the bias. Okay, and you usually use the activation function, which is generally introduced to introduce a nonlinearity in the calculation. Okay, so this also comes from the regular neural networks domain, but usually in the CNNs, and typically nowadays CNNs used activation function called rectified linear unit, or ReLU, which if I have to just draw how ReLU looks, is something like you have this one. So the ReLU will look something like this. Okay, so ReLU will be something like this. So this is like 0. And so in the positive, it will have like X, while in the negative, the value will be 0. So this ReLU activation function was actually first used by Alexa. It was found to be like immensely successful compared to some of the other activation functions. There are other activation functions of, let's say, like sigmoid or tanh, which looks something like this, or S-shape curved. Okay, so this is like tanh, while like sigmoid function is something like just this. Okay, so sigmoid function varies from 0 to 1, while tanh varies from -1 to +1. Okay, so usually the sigmoid function, this activation function, is introduced to introduce a nonlinearity in the entire calculation. So you have this nonlinearity calculator at each of this location. So what it will do is, now it will, as I had also showed in the previous card image, that the same filter will convolve through image. So at each location it will do this matrix multiplication, and it will do this multiplication constantly throughout that entire image. And after that you will get what is called a feature map or activation map. So since this blue filter was orange filter was used, so therefore the activation map that I'm getting is consisting of the I have shown in the orange color. So now what happens is, usually you do not have just like one filter, you have like multiple filters. So what does it do is, like, let's say like one filter will be looking for like edges, another filter will be looking for like corners, other filter might be looking for something like circles, or other filters might be looking for something like rectangles there. Okay, so what it will do is, like, there will like another filter, like multiple filters. So now this like blue filter, which will consist of different weights compared to the orange filter, will also convolve to the entire image, and then it will get a different activation map, which I'm showing now is the blue color, because this has been obtained from the blue filter. Okay, and this will go on, like, depending on the number of filters that you will use, the number of feature maps that you will get. Okay, so if you are using the n spatial filters, then you will get like n feature maps. And as I said, like, each of the spatial filters will work towards finding out the different features. Like, let's say like one will find out the corners, one will find out the edges. One problem that has been like seen is, like, you don't know like what each filter is specifically trying to find out. It looks something like a black box, but although like there has been like some researches showing like visualizing what each of these features does, and they have actually found out that the lower layers actually tries to find out all these like edges or corners. Okay. So now let's look further into like what will be the height and the width of this activation map. Okay. So to get this, like let's say we consider even a much more smaller image of, let's say, like 7x7. I am right now just ignoring the depth, because the depth will be like, if you have like a 3-dimensional, after like just assuming this 5x5x3, you will just get like a 1 dimension here, the width. Okay. So let's say like a much smaller scale where you have a 7x7 image. Okay. So in the first, you had your spatial filter, which is a 3x3, will be going right at this corner, and it will do this matrix multiplication. It will output like just one value from this filter at this location. Then it will shift next just to one stride to the next pixel. So it's exactly something like a sliding window thing, and we'll get like another output value. Okay, and this will continue throughout this entire image. Okay, so let's say like how many times that it can go through in this one. So you will have first one which will go from here to there, then the next one will go from here to there, and then the next one will be from this location, and then here, and then finally you have the final layer here. Okay, so in the final one you will have something like this, and then there is like no point in like shifting more. Okay, so the number of unique positions that I will get in like this in X direction is like 5, like 1, 2, 3, 4, 5. Okay, and similarly in the width also it will be like same. You have this, so you will shift like one location here, and then similarly you shift down. Okay, at each point you will find out like one value. So a 7x7 image, after convolving with 3x3 filter, it will have a 5x5 activation map. Okay, but now let's look into like whether this thing will remain same every time. Okay, so let's say like you have again the 7x7 image, but instead of shifting through 1 pixel, right now I can shift to like 2 pixels. So like there's no necessity that you need to only shift through like 1 pixels. Okay, you can shift as many pixels that you want. So the number of pixels that you're shifting is actually called a stride. Okay, so here you have a stride equal to 2, which is I'm giving here as like S. So in this case, if you have a stride of 2, so this is the second position, and the last position will be actually, now if you shift, the last position will be in this location. Okay, and after that you can't shift more. Okay, so if you have a 7x7 image, a 3x3 filter with a stride of S, so the activation map that you will get is a 3x3 feature map or activation map. Okay, so if we want to like generalize like what a given image, a given spatial filter, and a given stride, what will be the activation map size? So let's say we have the image given as like I. So always, usually we go with like square images. Even if it's a rectangle, we just resize it to square. So let's say we have the width and height equal to I for the image. For the filter size and the width, we have F, and the stride is like S. So the activation map output will be I minus F by S plus 1. You can just see like, okay, so 7 minus 3 by 2. So 4 by 2 is like 2 plus 1 is 3. Okay, and if you also just go with like stride equal to 1, you will see that, okay, so 7x7, 3x3 filter, it will give like 7 minus 3 by 1, 4 plus 1 equal to like 5. So this is the generalizing like what will be the activation map output. Okay, so but one of the issue that has been with convolution layers is usually if I go with like this feature map size, so it reduces like too fast. So a 7x7 image with a 3x3 filter, it will now get reduced to 5x5, and then if you have 3x3 filter again, then it will just immediately reduce to like 3x3. So usually from the bigger image, it like very fastly it reduces, and it doesn't help in learning the features. Okay, and not usually like people go with like 3x3 or 5x5 because of, again, the same thing on local receptacles, that you have some things here. So this immediate neighbor is comprised of like this location. So usually you go with like 3x3 or maybe like 5x5, although like 1x1 is also like possible. Okay, but since this size gets reduced like so fast, so therefore it has been found that it doesn't work too well in learning the features, because right in the next layer, I'm reducing the dimension by quite a significantly. Okay, so what is the alternate that we can use? So what we use is something called a padding. Okay, what padding helps is it helps to preserve the size spatially. Okay, so what do I mean by preserving the size? Let's say you have again the 7x7 image. Now you pad with using this green layer. So usually in this green, every time is given as like 0. So no other value instead of like 0 is like given. So it usually padded like 0 values. Okay. So now let's say I have like padded this with like 1 pixel on each of the sides. So right now the 7x7 got converted into like 9x9 using just this padding. Okay. So now if you have this filter of f cross f and stride of okay, just wait, can you squeeze this now? Yeah, I think. Let me confirm if you're not able to see the screen. Okay, I think you are able to see. I just did this hiding out this something which is showing here. Okay, so if you have this filter size of f cross f and you are using a stride of like 1, then the padding that is required is f minus 1 by 2. But if you see with this padding, then the output that you will get from a 7x7 image with a 3x3 filter will be again a 7x7 image. Okay, because now it will be going through here, then like one through like in this location, something like this. It will continue and ultimately you will get like a 7x7. So this padding helps to preserve the size spatially. So even a 7x7 after converting to a 3x3, it remains a 7x7. So it helps to alleviate that issue that I pointed out, that the size is like reducing like too fast. Okay, and it usually done with like 0 values, so that like ultimately when you're doing the matrix multiplication, anything multiplied by 0 for like this location will be just 0. So ultimately this at this location, the multiplication will be just affected by whatever is a pixel size in like this 4 pixels, and it will just give like 0 for this location, and this output will come out to be in this location. Okay. So if I want to just summarize the convolution neural net convolution layers, so usually if you have an input volume of size like W1, H1, and D1, which can be the original image or it can be the feature maps from the previous layer. Okay, so you have a filter size of like f cross f, which usually takes like 3x3 or 5x5 or 7x7. You have a stride, let's say like S, which usually takes like 1 or 2. The number of filters that you can use, as I said, like multiple filters are used of like this orange or blue colors that I was like showing. Usually they have found like computation, it is efficient that the number of filters are in the orders of like 2. So therefore they are used something like 32, 64, 128 or 512. It's just for computational efficiency. They are found to be working better if you are in the multiples in the orders of 2 to the power 4, 2 to the power 5, something like that. Okay. And the amount of 0 padding that's required, usually they take like 1 or 2 or as many as required depending on the stride and the filter size. Okay, so now with this, the output volume size will be W1 minus F plus 2P. So this is exactly same as like, as I told, like I minus F by S plus 1 that I just previously just showed. So this is the same thing, just we have this 2 times padding, because padding is applied in both the upper and the lower and the right and the left. Okay, so the output volume size will be this one, W2, then H2, and the D2 will be always be equal to number of filters that we are using. So you have like n filters, so the output volume size will be n. Okay, the number of weights that you will have for each filter will be F cross D1, because this filter size will actually be F cross D1, because as I said, like this filter will be through the entire depth of the input volume. Okay, plus 1 is for the bias. Okay, so the total weights will be then actually like multiplied by n, because you have like n filters, so like n weights and like n biases. Okay, so I have looked into, and we have said the CNN basics. There we had like 3 important parts. So we have looked into this local receptive fields, which is taken using this convolutional layers, which are the spatial filters. Okay, and you have the shared weights, because the same weight is used throughout across the image. Okay, and now they had like another important part, which was called subsampling or pooling. So let's look into like what is subsampling or pooling. Okay, So let's say like you have the 7 here, okay? This is also from this handwritten digit recognition case when you, from the MNIST data set, okay? So now let's say like you have right now, like find out like these features, okay? So what does 7 comprises of? It comprises of an edge here, a corner here, and also an edge here, okay? So these are the important parts of if I have to like distinguish a 7. But note like this exact location is not too much important of where the 7 will start. I can write 7 something like this also, okay? So many people write it like in different little way. So the important part is that there will be one edge here, one corner in at around this location, and another edge somewhere in the middle bottom, okay? But this exact location is like not too much important. So once we have found these features, but rather we need to downsample is maybe like at like this region and one edge was present, and in this region like one corner was present, in this region nothing was present, whereas like in this region this edge was present, okay? So like once we have the features are detected, exact locations are obviously not required. On the contrary, it might be harmful because they might shift a little bit like here and there. Okay, so 7 can start from like here and the corner can be somewhere like here, okay? So subsampling helps to resolve this issue. What it does is, I will just tell you how the subsampling does, but it operates over like each feature map independently. So if you have a 32 cross 32 cross 128, so 128 is the depth here. So it will be doing that for each of these layers. So the output will be again of the 128 because it is done for each of the layers separately. But what it does, it will be making the size smaller. So if you have a pooling or filter of like 2 cross 2 with a stride of like 1, it will just reduce to half, okay? So 32 cross 32 will reduce to like 16 cross 16, which makes it like more efficient towards its translation, and also because like much more manageable. So let's see like how actually like pooling is, okay? So pooling can be done in like different ways. The most popular way that pooling is done right now is called the max pooling. So and it's like very simple. So let's say you have this original image and you are wanting to doing the max pooling. So you have maybe like this location of this this blue region of 4 cross 6, 4, 6, 12, and 5, okay? So at this location, I'm finding out what is the maximum value, and I'm putting 12 here because 12 is the maximum, okay? So now I'm shifting 2 pixels and I'm going into like this location. I'm finding out what is the maximum value. It is 8, so I'm showing here, okay? Similarly, for like this location, gray region, we have the maximum 13, and for the orange region, the maximum is like 8. So you see that instead of having the exact location of where 12 was present, we have reduced into a smaller region. It's still at this corner, the top left corner, but we have now reduced of like where 12 was present at the second location to just at like in one location. So this is what like pooling does. So instead of the exact location, it goes into a much more in smaller dimension how it does, okay? But this is a max pooling. You can do other forms of pooling also. So let's say like average pooling, so finding out what is the average and putting it there. And there's something others called L2 long pooling and every other things. But however, like these days, max pooling is the one that is like mostly used. Although in like LeanNet 5, they didn't use max pooling at that point in time. They rather used again some sort of like weights and bias to learn like how to reduce this region of 4, 6, 12, 5 to something like instead of 12, they will have like a different number, which will be learned through the weights, okay? But these days, max pooling is the one that is being used. Okay, so if I have to look into the pooling layers, so if I have to just summarize, so the input volume size, if it's a WH1 and D1, so and if it has like two hyperparameters of the filtered size and the stride, okay, the depth will be like same as the D1. So the output volume now will be like the D2 will be equal to like D1 because as I said, like the depth remains same. So this is a general thing of like with the stride of like S and filter size of SF, what will be the output. And if you look into the way that it was in convolution layers, just since we don't have this 2p, since In pooling, we don't go with this padding. That's why we don't have just this term here. Another important change, usually if you're going with this max pooling or average pooling, you don't need to learn like any weights because it's just a maximum of that location. Okay. Whereas like in convolution layer, fundamentally the main difference is obviously that it has to learn the weights. Okay. So we have now looked into this. So this is actually the LeNet 5 architecture, which was proposed in Ian LeCun's paper. So it consists of this convolution and the subsampling layers multiple times. So first convolution, then subsampling, then again convolution, then again subsampling. Then it consists of something called a full connection. Okay, so what is full connection? Full connection is nothing, but it's just simple the regular neural networks. So what it does is that whatever input volume that you had from the previous layer, you squeeze into like one layer. So if you have like 5 cross 5 cross 3, you convert it into a single vector of 5 into 5 into like 3. Okay. So with the single feature vector, now you just go with the simple regular neural networks that is being used. And usually in the last layer, they use a softmax activation function, which is usually, if you look into a little bit of logistic regression or multi-class logistic regression, is the same one as like sigmoid function, but it's just the use for classification purpose to get the final class probability. So softmax activation function is usually used in the very last layer to give like what is the class probability for each of the class. Okay. So in a LeNet, this last layer will have like, they will give out like 10 probabilities saying like, okay, what is the probability of it's a 1, what is the probability of it's a 2, what's the probability of 3, something like that. Okay. So this shows the entire thing of CNN comprises of. Okay. So now I want to go into how to find out this architecture. Okay. So I said like these consist of 3 basic layers: convolution layers, pooling layers, and a fully connected layers. And usually how the architecture is made, they consist of consecutive layers or one or more layers of convolution followed by pooling layers. So it can be like conv pool, then again conv pool. It can be even like conv pool, something like that. So after this entire multiple sequences of this convolution pooling layers, finally towards the end, you will have this fully connected layers in the last few layers of the architecture. But also in the architecture that I showed before, and I will also go into this. Okay. So this is the LeNet architecture, which was proposed by Ian LeCun. So if you look into it had this input image size of 32 cross 32. So it had this convolution, first convolution, which is given as like C1. Then it had a subsampling layer of the S2, which is given here. Then you had the C3 convolution layer, then again a subsampling. So conv pooling or subsampling, then again conv pooling, then again a conv. Then finally, you have, as I said, that you have this fully connected layers. So the final fully connected layer will be the output, which will be a 10 dimension, saying like what is the probability for each of the class. Okay. So this just shows the entire details of like if you have the number of feature maps. So he used the feature maps of 6. The input size was 32 cross 32. The filter size was 5 cross 5. So if you, as I had already told you what is the formula, if you just put it, you will see that it's 28 cross 28 with a stride of like 1. So the number of weights that you need to learn is 5 cross 5 plus 1 for the bias. And since they had like 6 filters, so therefore 5 cross 5 plus 1 into like 6. Okay. So similarly, it went on with the subsampling layer and then with the convolution layers. Okay. And the major thing that I wanted to show here is if you look into in the initial parts, the number of weights that it needs to learn was not too much, whereas finally in the later layers, once this fully connected layers comes, then the number of weights that you need to learn is like significantly higher. So instead of like 150 or like maybe like 1,000, it had something like 48,000 or 10,000. And that is one of the main thing that has been like seen in like fully connected layers. It has too many weights that it needs to learn. So in a later layer, different architectures that was proposed later, you will see that they try to do away with this entire thing as fully connected layers except the last layer. Okay. So in total, it had approximately like 60,000 weights of this 32 cross 32 image. Okay. So let's look into the which was actually, as I said in the starting of this presentation, that this was actually proposed and came out winning this ImageNet challenge in 2012, and then ultimately bringing all the revolution in the deep learning. So they were using the almost same task, same thing that LeanNet used. Only thing that instead of this activation function of sigmoid or tanh, they were using a rectified linear unit, which I also showed like before how it looks, and it was found to be working like much more better compared to the sigmoid or tanh activation function. They used like GPUs, and it took approximately like 5 to 6 days of training on 2 GPUs on parallel. At that point of time, the GPU memory size was not too much. That's why they had to use like 2 GPUs. Right now, the memory size has increased significantly in the GPUs. But you can just see like the amount of training was like actually very long, and still now it can be like multiple days that you need to train your model since you have a large scale model. But once you have the model trained, then the inference time or predicting the label given an image is like very small. But training takes a significant long amount of time. Okay. So let's look into how this AlexNet architecture looked. So again, you can see here, this consists of the same pattern of convolution pooling. They had something called normalization, which I will not be going through here. And it is also not used in the later architectures also. But the broad overall thing was conv pull, then again conv pull. Then they had like multiple convolutions, and then with the final pooling. And then later you have this fully connected layers. Okay. And the number of features that you can see here was previously like 96 and 256, and gradually as the size, so if you can see the filter size is reducing, 11 cross 11 to 5 cross 3, then 3 cross 3, but the number of feature maps that you are using is gradually increasing in the later layers because they have to learn like more important higher class features. Okay. So if you see here, I can just again show like this is exactly using the same formula that I showed before. So the feature map size will be, if you just go into the formula, you will just get like 50 cross 55 cross 55, and the volume will be like 96 because there are like 96 filters, and approximately the number of weights that you need to learn is something like 35,000. Okay, and this like went on. So in like, but the main thing is if you look into the max pooling now, it has like 0 weights because it was using the max pooler, which do not need any weights to learn. And then gradually, if you like see, like in the later layers, you apply the same formula and you see that the number of weights actually needs to learn gradually increases from the 35,000 to 307,000. One of the primary reason because the number of filters that you need to learn is increasing in the later layers. Okay. So I'm applying just the same formula here of this I minus f plus 2p by s plus 1. Okay, and the output volume is gradually reducing from 227 to 55, and 27. And using the padding, it remained same 13 cross 13 here. So you see the padding is being used 1 cross 1, 1, 1, and the filter size now remains same. And then these are the number of. But right now, if you can see that once the fully connected layers comes, instead of this 400,000 or 800,000 weights, it just blows up to something like just in like an approximately like 40 million. Okay, so that has been one of the main thing of like the fully connected layers has a lot of weights that needs to be learned. Okay, but in total they had like almost like 61 million weights, and if you see like if you have to learn like so many weights, chances of overfitting are like very high. That's why we needed a much larger scale data set, which like ImageNet proved. With the handwritten digit recognition data set that was down there, it was a much more smaller data set, and all the other data sets that were also available was much more smaller. But ImageNet was much more larger data set, and therefore even if we have like this large number of weights that needs to be learned, still overfitting is not an issue. Although like there are still the ways overfitting happens, and there are different techniques that are used to handle overfitting. So now I can just go through the next one, which is the VGGNet, which is actually the second runner-up in the year 2014. So there was like another winner, but the main thing why like VGGNet became like so popular because it was like very simple and intuitive design. Beforehand, like people were like so much confused regarding the number of, if you like see in the last one, like the number of filters that they are using, then the number of strides that they were using, then the number of features that they are using. There were like so many hyperparameters that people are not sure like what will be the filter size that we will like usually go through, how many feature maps to use, and then there's so many different combinations that people can try out. What VGG used was that they had a very simple and intuitive design, which like much lesser hyperparameters or much lesser complicated design of how many filters to use. So they used a small uniform filter, so 3x3, and only thing that they used was they increased the depth. So they had like different architectures that they used, so that is shown as A, B, C, D. So ultimately D and E became more popular because these consist of like 16 layers, so then that's why it was called a VGG 16. The E consisted of 19 layers, and it was called like VGG 19. Okay, and you can see that how it is present. So conv3 basically means a convolution of 3x3. 64 means how many filters that they are using. So 3x3 filters of 64 numbers. Okay, so you can see that they had the same 3x3 applied throughout this entire, every time that they were using a convolution, they were using just 3x3. So nothing of the 5x5 or 11x11 or something like that. And after like multiple convolution, 2 convolution layers, they were using the max pooling. After max pooling, they were just doubling the number of filters that they were using. So instead of 64, now like 128. Then they again had a max pool layer. Then they just double it to like 256. And then they had like 3 convolution search, then max pool, and then they again convert it to like just double it to 512. So it's much more simpler, and they found that it works as good as like AlexNet, or even like much better than that also. Like AlexNet has something like 15%, while this top 5 error was 7.3% in the ImageNet. Okay, the number of parameters that went on here was from 60 million here to something like 150 million, because they had like much more number of layers. Okay, but what they also showed is like, if in the previous ones they were using different filter size of at some point in time 3x3, at some point in time like 7x7, something like that. But they showed that if you are using rather like a same filter size but multiple amount of time, so instead of using like 3x3, 2 times is almost equivalent to using just one 5x5. Or if you use 3x3 filter, so it's almost equivalent to using a 7x7. On the other hand, it was actually shown that it like, first of all, it has like much more lesser weights that needs to be learned, because 3x3 is something like 27, whereas 7x7 is something like 49. Okay, so the number of parameters that you need to learn is like much smaller. And on the other hand, it was seen that if you go with the smaller filters, but smaller filter size, but the number of filters that you are using are larger, then it learns actually like much more better. Okay, so and that was the reason why like VGGNet became like so popular, although it was not the winner, but it became like very popular because of this intuitive design. Still now people use it a lot. Okay, so there has been like many other architectures that has been like used by people. So in 2014, the GoogleNet, or the Inception, was the winner, which was almost like 22 layers deep, but they didn't consisted of any fully connected layers. So therefore, the number of parameters got reduced to only like 5 million instead of the 140 million or something like that, which the VGGNet had. Okay, but still at that point in time, they had something like 22 layers, 19 layers, 16 layers. In 2015, they came out with this was actually the ResNet that came out from Microsoft, which won, and it was, instead of this 22, they had like 150 layers, but still the inference time. So inference time is you just give an image. So there is a training and the inference time, or testing time is the inference time. Is a given an image, predict like what is the class. So inference time was much more faster, although it was a 152 layers deep. I'm not going to the details, but if you are interested, you can look through this paper. In fact, like ResNet paper is the paper which has been the most cited paper as of now. Okay, and the error rate that they reduced was like immensely compared to all the other error rates that was like beforehand. Okay, and in this year they won all the challenges. Basically, ResNet won all the different challenges that were in ImageNet. Okay, and in 2017 there was another one that came out, another popular called MobileNet. It had something like less accuracy. So the top 5 error rate, as you can see, is like not as good as like ResNet or like the GoogleNet. But the important thing that it had, what it has like much lesser parameters, and it can be used for like mobile or all this embedded vision application where it's like very difficult to use like GPUs. Okay. So that was the reason why like MobileNet also is like very popularly used. Typically, if you are using in mobiles, where like you don't have GPUs, but still you need to like work very fast. Okay. So this is a comparison graph that shows like, so you can see that there are like different, so many architectures that has been like proposed. The x-axis here shows the number of floating point operations that needs to be done. So this shows how much computation intensive a model can be. The larger is the size of the circle, the more number of weights that it needs to learn. So you can see that VGG, the number of weights that it needs to be learned, and you have this ResNet, the number of weights that they had to learn like much more smaller. Okay, and they had like this MobileNet, which is like even much more smaller operations that needs to be done completely. So this CNNs. Okay, one of the main thing is all these deep learning models are very data hungry. Okay, so the immense amount of the labeled data, and getting such labeled data is extreme time consuming and expensive also. So just to find out like which are the cars and then label them manually, and then using that label data set will become like extremely expensive if you have to do like on a very large scale. Okay. So therefore, and also on the other hand, training the deep models are like very computation intensive. As I showed that it takes like multiple days, even in the parallel GPUs to run the models. Okay, even like multiple weeks can take. So how can, and not everyone can have like such a large scale data or a large scale GPUs. Okay, but what they can use is something called transfer learning. Okay, so transfer learning is the thing that was found to be like very useful in deep learning, and that was also one of the main reasons why like deep learning also became like so much successful in the different areas. Like it used the information that was extracted from large scale data. So the large scale data is the ImageNet, because that is one of the large scale data set that has been like available and right now. So you use that information that you have from that model that you have learned from the data, and then you fine tune that or use that same information to learn a little bit different task. So to give you an example, let's say like right now, even if as a child knows how a car looks. Right now, if a child has to know how a bus looks, it's not that it will like completely unlearn how a car looks to find out like how a bus looks. They are like quite similar to each other. Car has a windshield, car has wheels. Similar, bus has a windshield, bus has also wheels. Okay, only their shape is different, their size is like different. Therefore, this information of how the windshield is, how the wheels are, they are like still important. And that was also found in how the humans learn. And even when like in CNNs, that they are found that the information that has been gained on maybe like learning a car is useful when you are learning a, let's say like a truck or maybe a minivan or something like that. Okay, so there are 3 different ways of how transfer learning can be used. They are called like fixed feature extractor, fine tuning, and feature model. So I'm going to each of them like one after another. So what does fixed feature extractor means? So let's say you have this AlexNet architecture. So you have this full normalization and all these other things. So what you do is that in the fixed feature extractor, you just remove the final layer, which is the final output layer usually. Instead of that, you just extract the features from this all the previous things. So the final one that you get from the FC7, which will be a 4096 dimension, you use this as a feature extractor. So you take your image, you go through this entire of this convolution pooling and everything, and you get the features. Okay, and the features that you have, then you use any sort of a classifier. It can be something like a SVM or a softmax classifier to learn your final classification model. So and you can use like any model. You can use like VGG, you can use ResNet or MobileNet or any other models that you have. You use a model, you just remove the last layer, which does actually the final classification. In this case, it was 1000 class, so it was the 1000 class vector. So you remove this final layer, you have whatever was before, you use that as a feature extractor. You extract the feature and you push that to a normal traditional classifier of, let's say, a support vector machine or a softmax. Okay. So in fine tuning is a little bit different. So in fine tuning, what you do is like you actually, instead of just extracting the last layer and learning a different classifier on the features extracted in the last layer, rather you freeze all the previous layers. So all this given as a green, the weights are fixed. Only the last few layers, you learn the weights using backpropagation, which is actually the fundamentals of how neural network learns these weights. Okay. The reason why fine tuning is used, because it has been also showed like these initial layers find out some of these generic features of, let's say, the edges or blobs or the corners. Okay. So you need to still use those. So you freeze those weights, and only in the last few layers you learn the weights. In fixed feature extractor, you are just using here. Okay. While in fine tuning, you can do like a little bit extended of the fully connected layers, or even if you want, you can go further up if you want. Okay. Because also the final layers are the ones which are like more specified towards specific classification tasks that the people are doing, of, let's say, like finding out exactly like how a car looks compared to how a bus looks. Okay. The third is a pre-trained model. So in pre-trained model, what it does is it comprises of these initial weights that they learn from the ImageNet. So they just start off with those weights, okay? And then they build a completely new architecture. Only thing is the initialization that you do of these weights, you start off with the initial weights from trained from ImageNet, okay? You start off this initial weights, because initialization of the weights is also a very important thing, and how your accuracy is depends on how you initialize your first weights, okay? So in the very first layers of, let's say, this file, 55 cross 55 cross 96, like what was the weights that you need to use in the convolution layers? So those weights, you start off with this ImageNet trained models, and then you build the final, you build your own architecture completely, and then you train the entire model. So here the only difference is that the initial weights are being started from the image, and that has been also found to be like very successful compared to if you're using weights from the very beginning. Okay. So if I have to just give like a practical summarizing everything of, let's say you have like a new data set, which is like very similar to the original data set, but the new data set is very small. So therefore, you do not have the capacity to learn a CNN model. Okay. So at that point in time, you use a fixed feature extractor to do your final classification. But if your new data set is like large, but on the other hand, it's similar to the original. So let's say like the car, instead of cars, you are finding out just trucks or buses. Okay. So what you do is like you just fine tune one or more layers, because right now, since the data set is like large, so you have the capacity to have like more weights learned. Okay. So on the other hand, the new data set is small, but it is also completely different from the original. So you cannot usually go with learning a model, which is a CNN model, because it will like definitely overfit. So you have to go back to the shallow machine learning models or something like SVM classifiers. Okay. But on the other hand, if new data set is large and it's like very different from the original, then you actually go with the pre-trained models, where you just initialize the weights in the pre-trained models, and then you have your full architecture where you are learning the weights. Okay. And usually when you're doing this transfer learning, you have like smaller learning rates, because you have already a good starting point. So therefore, the way to learn will be like to go with having like much smaller learning rates. Okay. So that is the complete overview that I had on like CNN, starting from the convolution layers, the basics of pooling, how they are used, and then finally the different architectures, and then finally like how to use in your own models that you want to like learn. So right now I'm open to any questions, and thank you everyone for listening.
Thank you so much, sir, for such a comprehensive presentation and explaining the basics so well. I'm sure the participants would have gained a lot from it. Also, there are some questions from the side of participants which I would like to ask you on behalf of them.
Yeah, sure.
So should I?
Yeah, sure.
Okay. R. Shanti Vengadeshwari wants to ask that can a simple civil engineering application be explained as in a truss?
Okay, so here, if I look into, there has been like many other literatures that they have used these cases of these neural networks of, if you want to do one of this major case of, let's say you want to do like a structural health monitoring. Okay, so in those cases, CNNs have been used, but I would say that the major advantage of using CNN is wherever you have images. Usual other types of, let's say like SVM or those things works well if you are working on, let's say on just on fixed features or something like that. But when you have to do anything of this classification or those things on images, then the main thing of where CNNs are actually like very useful.
Okay, Vidya Priya wants to ask, is CNN better than SVM?
So I say like it depends on the task you are doing. So, and in fact depends on the amount of data set that you have. So if have a smaller data set, then no way that CNN can work like well, because the CNN's main thing is that you have a large, okay. Well, like SVM works well if you have a smaller data set. Okay. But on the other hand, also places where like CNN works better is when you have the images. When you have a large set and you are working on images, then like CNN will be working like always better. But if you have a smaller data set or you have a different problem, then SVM will work better. So SVM was a state of the art in the pre-deep learning era, but right now in images, CNN works much, much better compared to like SVM.
Okay, another question is also related to SVM. Prachi Joshi wants to ask you that if you can explain SVM a bit.
Okay, so I think like it will go too much if I just want to like explain SVM. But what it does is rather you have something called like kernels. In kernels, you have like these different kernels called a radial basis function or something like that. I'm not going through that in this specific lecture, but if you're interested, I will say like you can go through some of the lecture videos which are from Andrew NG in Coursera, and also in YouTube you will get his lectures, which are like very good in giving you the basics of the support vector missions. Okay.
Thank you, sir. Also, Lauren Satapathy wants to ask, is there any application of CNN in structural engineering except structural health monitoring?
Okay, yeah. So anything that you can think of using like images that has like CNN to be applied. Even what people do is like, let's say you have just maybe the not images, but you can transform into images. Okay, so I can give you some examples of, let's say you want to find out like each of these locations of where like the data imputation needs to be done. There also like CNNs can be used. But any sort of like applications where you convert, you can convert your data set into images that you can think of. But as of now, most of the applications has happened actually in structural health monitoring, because there you have all this damage detection and other things where you just need like images extracted and you want to find out like how they're like, how much crack they have happened or something like that.
Okay, thank you, sir. Also, there are some more questions, if you allowed, so that I can ask you on behalf of the participants.
Yeah.
Okay, Mohammad Yasin Bhatt wants to ask, what potential does the latest strides in deep learning in NVIDIA graphics card unlock? NVIDIA has been pushing DLSS very aggressively in the marketing campaign ever since the 3000 series came out. AMD is also working on it.
Okay, so yeah, like NVIDIA came out of this recent 3000 series. I would say like the main thing that they are doing is like you can have much more faster computations with this 3000 series. But if you're just going to like start off with some of the very basic things, then it doesn't matter. Even like I worked on for a long amount of time in 1080 Ti. 1080 GTX. Okay, that was working fine for most of the cases. Obviously, as they are working on improving them, for much more larger scale, these are like much more better. But if you are just making like small models or something like that with not large scale data set like image or something like that, then usually they will work like pretty same.
Okay, thank you, sir. Dr. Komal Mehta wants to ask, can you please discuss any application in the field of environmental engineering?
Okay, so in environmental engineering, actually, like I can tell you like CNNs has been used. So I was just having like one of my classes with in my IIT when like yesterday like one of the student had to like present, but they are saying like you have just an image and you want to find out like what is the ear quality. So in those type of cases, when you have that image, right from the image, if you want to find out like what is the ear quality, because the thing is like usually cameras are like very much like lesser expensive compared to any of the other sensors, and since cameras have like evolved like so much further, so therefore like they are like really useful in doing all this task of whatever you want to do in like let's say with the images. But there are I think like many other applications I am like not completely aware of because I am in the more in the transportation domain. But those anything that you can think of with the images, I think like there you can think like it will like really work. So let's say like waste segregation or like after the different type of waste that are down there, if you just want to like segregate there, also you can use CNNs.
Thank you, sir. Another question is also related to the field of hydrology, but I will just ask the question. Ratna Kumar wants to ask that linear time invariant convolution integral is used for direct runoff in hydrograph analysis. Is there any inspiration of CNN that is convolving filter with image with this convolution integral used in hydrology?
Okay, so I think unfortunately I have like not too much knowledge in hydraulics, so I will not be able to understand, able to also understand what is being like told here. Yeah.
Yeah, she's asking something related to direct runoff hydrograph in hydrology, of course. That's why I was avoiding her question, but she has asked many times, so I thought of giving it a try.
So I think like I am like not too much. Also, maybe I have to like learn a little bit more. But if I look into something like if you are doing some sort of the prediction task, because this runoff and everywhere like you do like a lot of prediction tasks, and so in prediction tasks usually there is another field of like deep learning, which is called LSTM or long short-term memory, which actually looks very good in all the types of prediction tasks. So like in transportation, we have like, let's say I have to predict what is going to be the traffic tomorrow or maybe after like 15 minutes. So we are like predicting something. So similarly, if you have to do like runoff, like what is a prediction, then you can use other software which actually does with LSTMs. Okay. Yeah, but I think like I might be like not too sure if it was the correct answer.
Okay. Someone wants to ask, just a second, wants to ask that how can CNN be used for pavement defect detection?
Yeah, so actually like that has been like used a lot. And if you like just in a presentation, I showed like one of the papers. I just showed briefly. Maybe I can just reshare. Okay, so if you look into this one, this Kupal Krishnan et al., which were actually trying to find out this pavement distress detection. So you had images and you want to find out like what type of crack it is. Then in those type of cases, CNNs have been found to like work very well. Okay.
Okay, thank you, sir. Kritika Avasti wants to ask why convolutional layers are not using 2x2 filter.
So one of the reasons why like that is not, it doesn't go with the even size, because of this like local receptive fields. So if you look into this 3x3, one of the good thing is that I was like showing here. So you have this center one, and whenever you go with the odd shapes, you are considering all the neighborhoods, which are just around like this pixel. Okay. So in those type of cases, that's why like in the local receptive fields, you usually go with the odd numbers rather than with even numbers.
Okay, thank you, sir. Ratna Kumar wants to ask that suppose in a remote sensing image, it has 3 bands. Then after convolving with one filter, 3 activation maps will be produced. Is her understanding correct?
Okay,
that's what she wants to ask.
Okay, so here I would say that if I understand the question correctly, let me just go through at this point in time. So you have this image, original image, which is of the depth 3, which is of 3 channels RGB. Okay, so always the filter size is also of the same depth. Okay, so this is also like 5x5x3, whereas a 32x32x3. Okay, so once you do this convolve, just with this location here, with this one activation map at one location, you will get like just one value. Okay, so one activation map will give you just one value. Okay, so if you have n filters, then you will get like n depth. Okay, so the depth is equal to the number of maps that you are using. So it doesn't depend on the original depth.
Okay.
So I hope that is able to answer you.
I hope all the questions and queries of the participants are resolved. Thank you so much, sir, for your valuable time. We are extremely grateful for you being here, presented so well and explained the basics so well. Thank you so much. We'll be having you again tomorrow, and hopefully it will be an interactive session as well.
Yeah, thank you everyone. Thank you for doing this presentation.
Sakiba, can you request sir to share the presentation?
Yes, sir. Yes, sir. Sir,
Okay,
can you please share your presentation with us so that the participants can have that for their reference and whenever they need?
Yeah, sure. I will just send it to. I have the email ID of Professor Dar, so I will just maybe like share with him, and he can pass that on.
Okay, sir. Thank you so much. Thank you so much. And
thank you very much.
Yeah,
thank you for the session. Then I am for the day at 11:30. I'm requesting you all to please join in around 10 to 15 minutes before, and as usual, follow the rules. We will be sending you the YouTube links and the recording of the session soon, and take care till then. Thank you so much.